Hello students, welcome back. Today we're going to be continuing talking about derivatives, and today's topic is going to be derivatives of polynomials and exponential functions. So let's recall the definition of the derivative, right? So the derivative, f prime of x, right? Or it's the same thing as d of f dx is equal to limit as h approaches 0 of f of x plus h minus f of x all over h. All right, so we're going to be using this definition to prove certain formulas for the polynomials and exponentials and some constant functions. So our first equation that we want to prove is, of course, the following. So we want to prove that the derivative of a constant function is 0, right? So essentially what we're saying is that f of x is equal to c, which is a constant. Okay, so that means what are we going to have? F prime of x is going to be limit of h approaches 0. So we don't have x here, right? It would just have a constant. So it's going to be c minus c over h. So that's equal to limit of h approaches 0 of simply 0 over h, which is equal to limit of h approaches of 0. And that's equal to 0. All right, so perfect. We proved that formula. Okay, now our second formula is going to be the following. So now let's take a derivative of just x, right, of a single x. So that means that the derivative of x is equal to 1. So let's go ahead and prove this. So f of x equals to x. Okay, so that means f prime of x will be equal to limit as h approaches 0 of f of x plus h, which is going to be x plus h, right, minus f of x, which is x, divided by h. So that's equal to limit of h approaches 0 of x plus h minus x divided by h. So clearly we can cancel out x and x, and we will have that limit of h approaches 0 of h over h, which is equal to 1. Right, perfect. Now, well, let's continue our pattern. Let's go ahead and now prove. So we're going to prove that dx of x squared, which is equal to x squared prime, is equal to 2x. Okay, so let's go ahead and prove it. So we have x squared, right? Our f of x is equal to x squared. How about our f of x plus h? That will be x plus h squared. All right, perfect. So if we expand this, right, we're going to have x squared plus 2xh plus h squared. So now let's go ahead and plug it into the limit definition. So we will have limit of h approaches 0, right? This is our f prime of x. Which is equal to limit of h approaches 0. So we're going to have f of x plus h minus f of x over h. So that's equal to, we're going to have limit of h approaches 0. So f of x plus h is going to be x plus h squared, right? So it's very important. Majority of students are making mistake here, forgetting to put the square outside of the parentheses, right? Because we're taking the square of the entire thing. It's two different things if we square each term and if we square the parentheses. Minus x squared all over h. So if we open up the parentheses as by the rule above, by this, we will have x squared plus 2xh plus h squared minus x squared all over h. Right, let's remember that our main goal is to cancel out the h in denominator. Right, this is the most important part about the derivative. So we're going to have x squared and x squared go away. So we will have a limit of h approaches 0 of f of x h plus h squared all over h. All right, let's notice that in numerator we do have a common term, which is going to be h. So if we factor out limit of h approaches 0 of h times 2x plus h over h, we can notice that h and h cancels out. So we're going to have limit of h approaches 0 of 2x plus h, which is equal to 2x plus 0, which is equal to 2x. All right, and so this solution is exactly equal to this solution. All right, perfect. Now, let's go ahead and prove the next one. The next one is, so we want to prove the dx of x cubed is equal to 3x squared. Okay. Now, let's go ahead and, again, recall a few things. So we have f of x to be equal to x cubed, and then f of x plus h, it's going to be equal to x plus h cubed, right? Don't forget the parentheses. So, by the identity of cube, right, x plus h cubed, if we recall from algebra, right, we will have x cubed plus 3x squared h plus 3x h squared plus h. All right, so now let's go ahead and find f prime of x, right? F prime of x and d dx is the same thing, right? Keep that in mind. So that's equal to limit of h approaches 0 of, so f of x plus h, right, is going to be x plus h cubed minus x cubed over h. So expanding the parentheses, we're going to have limit of h approaches 0 of x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed all over h. So again, let's see if we have common terms, and we indeed do. So this term and this term, so x cubed cancels out. So we will be left with limit of h approaches 0, 3x squared h plus 3x h squared plus h cubed all over h. So we do have common term in the numerator, which is going to be h. So we can go ahead and factor it out. So we're going to have limit of h approaches 0 of h times 3x squared plus 3xh plus h squared all over h. Okay, so h and h again cancels out. So we will be left with limit as h approaches 0 of 3x squared plus 3xh plus h squared. So that's equal to 3x squared plus 0, which is equal to 3 squared. And if we notice, this is exactly what we were trying to prove. Alrighty, perfect. So now let's go ahead and do one more power. We're probably already noticing the pattern, but let's do one more. So now we want to prove that dx of x to the 4 is equal to 4x cubed. Okay, so we know that f of x is equal to x to the 4. F of x plus h is equal to x plus h to the 4. And well, it's going to be the fourth order polynomial, so it's going to be x to the 4 plus 4x h plus 6x squared h squared plus 4x h cubed plus h to the 4th. Right, perfect. So now let's go ahead and find the derivative. So it's going to be equal to limit as h approaches 0. So let's plug in the parentheses already. We know what we are going to be plugging this one in minus this one. So let's do that. So we're going to have x to the 4 plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the 4th minus x to the 4th. And this is all over h. So clearly, x to the 4th, x to the 4th cancels out, and all of the rest of the terms have the common factor of h. So we're going to have limit as h approaches 0 of h times 4x cubed plus 6x squared h plus 4x h squared plus h cubed. See? Perfect. So now that's going to be all over h. So this and this cancels out. So we're going to have limit as h approaches 0 of 4x cubed plus 6x squared h plus 4x squared plus h. Plugging in, we have 4x cubed plus 0 plus 0 plus 0, which is equal to 4x cubed. Exactly what we wanted to. All right, so we probably already noticed, right, that the rule that we are trying to derive here is called a power rule, right? One of the most useful rules in mathematics, right? This is a power rule. And we are able to actually do a full proof. So there's two ways we can prove it, right? We can prove it by the simple factorization formula, right? That we can factorize, right? And then we can also prove it by using the binomial formula, right? Binomial formula from the probability and statistics, right? So by binomial theorem, we could have expanded our terms, and all of the terms will have the h. So let's go ahead and do. We're going to do both, right? So go ahead and do both proofs. So proof number 1. So we have to keep in mind the following formula. So we know that x to the n minus a to the n is equal to x minus a times x to the n minus 1 plus x to the n minus 2 times a plus x a to the n minus 2 plus a to the n 1. Okay, so then what we can do is we can do the following. So we're going to find the derivative at point A, right, which is A's arbitrary point. So we're going to have limit as x approaches A. So we're going to use the first definition of the derivative. So it's going to be f of x minus f of A over, right, x minus A. So that's equal to, right, that's equal to limit as x approaches A of x to the n minus a to the n over x minus a. So again, when we plug it in, right, clearly we have x minus a and x minus a. So that's what's going to be canceling out. So x approaches a of x minus a times x to the n minus 1 plus x to the n minus 2 times a plus dot 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 plus x to the a n minus 2 plus a to the n minus 1. Alrighty, and this is all over x minus a. So clearly, x minus a goes away. So we will just end up with the following. So we will have limit of x approaches a of x n minus 1 plus x n minus 2 times a plus dot 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 plus x a n minus 2 plus a n minus 1. So if we plug in a, we all gonna get the term a to the power of n minus 1. And if we sum up n terms, we're gonna get n. So that's gonna be equal to n times a to the n minus 1. Right? Think about it. Think about it. If you have a to the n minus 2 times a, that becomes a to the n minus 1. Right? So likewise, we can do here. If we have a times a to the n minus 2, it's going to be a to the n minus 1. Okay, so it's all going to be a to the n minus 1. So we can add them all together, and we're going to get n, a to the n minus 1. So a is arbitrary point. Okay, now if we do the binomial theorem, right, binomial theorem, it's going to be slightly different. So here we are done with this proof, right? We proved the formula, right? We can do it binomial theorem. So proof number 2. So by using binomial theory. So we know, right? We know that we can do it as f prime of x, which is equal to limit as h approaches 0 of f of x plus h minus f of x over h, which is going to be equal to limit of h approaches 0 of x plus h to the n minus x to the n over h. Okay, so by using the binomial theorem on the term x plus h to the n, we actually will get the following. So limit as h approaches 0 of x to the n plus n x to the n minus 1 times h plus n minus 1 over 2 x to the n minus h squared plus dot 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 plus n x h to the n minus 1 plus h n minus x to the n. This is all over h. Okay, so clearly, if we open up parentheses, x to the n cancel out. All of the other terms have h, and this one's going to be the only one with the h to the first power, right? The only one to h to the first power, which is perfect for us because we're going to have just, we will have limit of h approaches 0, so h is cancelled out if we factor out, so we're going to have n x to the n minus 1 plus n minus 1 over 2 x to the n minus 2 times h plus dot 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 plus n x h n minus 2 plus h n minus 1. Okay, and that will just simply equal to n x to the n. Right, so for binomial, slightly faster. Right, slightly faster. But there are two proofs. Okay? So now we don't have to worry too much about using limits, right? So let's go ahead and take a look at some examples. So example. So if we have f of x is equal to x to the 6, f prime of x will be 6x to the 5th. How about we have f of x is equal to 1 over x. How could we do that? Well, we have to remember the rule that it's the same thing as x to the negative 1. So that means n can be any integer, right? And besides the integer, it can also be a fraction, right? And we're gonna do we can do the same thing for the fraction, and we can do it through the limit. And we will do it through the limit first, and then any fraction will also behave similarly as the integer part. So, okay, so how do we take the derivative of this? So f prime of x is going to be -1 times, right? -1 times, so it's going to be x to the -2, which is equal to the -1 over x squared, right? So now we can do any fractions, right? Any fractions of 1 over x, right? As long as it's 1 over x, we don't have any other functions attached to it. Okay, so now for the square, it will be a little bit different, right? So if we want to prove that d dx of square root of x, right, which is the same thing as square root of x prime, is equal to 1 over 2 square root. I want to prove that. And well, of course, we can prove it by the power rule, right, because it works. But if we do it through the limit, so the limit of x approaches, not x, let's do h. So limit of h approaches 0 of square root of x plus h minus square root of x over h. So the trick here is to actually rationalize it. And we're going to be rationalizing by multiplying by the conjugate of this. So it's going to be square root of x plus h plus square root of x divided by square root of x plus h plus square root of x. So if we do so, we're going to get limit of h approaches 0. So in the numerator, if we distribute it, we're going to have x plus h minus x over h times square root of x plus h plus square root of x. So clearly, x and x cancel out. And then we will have that we have limit of h approaches 0 of h over h square root of x plus h minus square root of x. So now h and h cancels out. So we simply have limit of h approaches 0 of 1 over square root of x plus h plus square root of x. Right, so that's going to be equal to 1 over x plus x, which is equal to 1 over 2. And so now we proved, right? So now we know the power rule also applies to the fractions. Okay, and so, well, we can verify it, right? Square root of x prime is the same thing as x to the power of 1/2, which is equal to 1/2 times x to the 1/2 minus 1, which is 1/2 times x to the -1/2, which is equal to 1 over 2 x to the 1/2, which is equal to 1 over 2. Right, perfect, perfect. So once again, we're going to call the power rule for general, right? General version of it for any real number. So for any, if n is any real number, then we can just simply use this, right? So now we don't have to do the limits. We can simply use the general rule. So of course, now we can also do the proof that of the following. So if we are multiplying by a constant, this is very important, right? If c is a constant and f is a differentiable function, then if we have c times f, we can factor out the c before the differential, so we can first differentiate f fully and only then multiply the entire function, right? This is the key thing, the entire function by c. Okay, so let's go ahead and prove it. So we know let g of x to be equal to c times f of x. Okay, then we will have, well, g prime of x is equal to limit of h approaches 0 of g of x plus h minus g of x. over h, which is equal to limit of h approaches 0 of c of f of x plus h minus c of f of x divided by h, which is equal to limit of h 0 of c times, so I can factor out the c, right? F of x plus h minus f of x. And by the limit loss, right? By limit loss, we can factor out the c outside. So it's going to be c times the limit as h approaches 0 of f of x h minus f of x, right? All over h. So, and that is, by definition, right, that is the derivative. So it's c times f prime x. Right, so we proved it. Right, this is exactly what I wanted to show, and we did show it. Ready? Perfect. So now, example. Go ahead and do an example. So if we have d dx of 4x cubed, right, that's equal to, so it's going to be 4 times dx of x cubed, which is equal to 4 times x cubed prime. Right, you can use either of the notations. Okay. The reason why I use here d dx, because later on, when you guys watch the differential equations course, differential equation is going to use a lot of d dx. Right, and d dx is essentially an operator, and we gotta get used to it, so we better start getting used to it in calculus 1. So we're going to have 4 times 3x squared by the power rule. So that will be equal to 12x squared. Ready? So then the next rule that I will let you guys prove it on your own. So we want to prove, well, you want to prove that the sum of f and g, if f and g both differentiable, we can just distribute the differentiation. And essentially, that works out because of the limits, right? If you say, well, let's say sketch of proof, right? So you're gonna say let f, so you can say let h of x, capital H of x, is equal to f of x plus g of x. Okay, so when you do hx plus h is going to be f of x plus h plus g of x plus h. So you will get the limit, and you can separate the limit, so you will turn out to have derivative of f and derivative of. So that is pretty straightforward. So same thing, right? Exactly same way you can prove the difference, right? So here, limit, right, as h approaches 0, you will have f of x plus h plus g of x h minus f of x plus g of x. Right, so if you rearrange everything, you will end up getting f prime of x. So watch out for signs and don't make algebraic mistakes. Okay, so the difference rule is going to be as following. So if f and g are both differentiable, then we can use a difference rule, right? Which is pretty straightforward. So essentially, if you, example, right, if you have x squared plus 2x, right, then x squared plus 2x prime is equal to, so it's going to be x squared prime plus 2x prime is equal to 2x plus 2x prime, which is equal to 2x plus 2. All right, and then if you have 3x squared minus x cubed, right, then you're going to have 3x squared ddx, 3x squared minus x cubed is equal to d dx of 3x squared minus d dx of x cubed, which is equal to 3 times 2x minus 3x squared. So that's equal to 6x minus 3x squared. Right? Perfect. Perfect. So now let's go ahead and actually do an interesting thing. We can do the definition. Right? The interesting thing is essentially when the exponential functions were defined, right, were defined for the derivatives. It happened that number e was direct. So let's go ahead and give the definition. Definition of the Euler's number. Right, we were talking about it. We're using it in logarithms. But here is the official definition. So e is the number such that limit as h approaches 0 of e to the h minus 1 over h is equal to 1. Okay, this is such number. Okay, and the nice thing about the specifically x, it has the following property. So the derivative of e to the x is e to the x. So the derivative is itself, which happens to be extremely useful, right? Extremely useful in calculus. Next time we will talk about product and quotient rule. Thank you, students, and see you in the next video.